Hi everyone, so another video, I love saying that, another video, and this time it's on proof. This is the first installment of proof, because there will be one more video, but a little bit later, which will be proof by contradiction, um, which is much more hard, which is much more difficult than what we're doing now, alright? So I'm going to try and make this video fairly brief, because you're going to, hopefully it'll be self-explanatory. But there are three different methods of proof that we're going to do today, which is deduction, exhaustion, and counterexample. Okay, so first off, let's use deduction. So we're going to deduce that something's true. And with proofs, you have to be rigorous and you have to show every step. So I'll try my best to be as formal as possible to set a good example. So it says prove that n squared minus n is an even number for all values of n. Now there's a trick here to always apply if I were you. Okay, so prove that that's an even number. Okay, so if we know so I just got distracted. All right, so n squared minus n for all values of n. So that means n can be any type of number, and it is, they do mean an integer here, by the way. Okay, so if we first look at, so all the odd numbers that exist, okay, there's a way to express an odd number. So if we let n then be an odd number, 2k plus 1, right, where k is an integer. So this is might as well start with the good maths now, right? This funny looking z, this means integer. This like kind of weird euro sign looks a little bit like, as in the, the euro note, looks a little bit like, does it look like a euro? Yeah, a bit. It means like element of, okay? So it's saying that k is an element of the integers. So if n, and this makes sense that this is an odd number, doesn't it? Because if k was 0, n would be 1, so that's odd. If k was 2, sorry, if it was 1, n would be 3. If k was 2, it would be 5. So it takes care of all the odd numbers. So we would get n squared minus n is the same as 2k plus 1 squared then, minus 2k plus 1. And 2k plus 1 squared is 4k squared plus 4k plus 1. Subtract the 2k, subtract the 1. So we get 4k squared plus 2k only. We need to prove that it's an even number. If it's even, then it's divisible by 2. So as long as I can take a factor of 2 out, it's even. So hence, for n odd, n squared minus n is even. Okay? Since 2k squared plus k is an integer. Right? Fantastic. Now we've done the odds, but we need to do the evens. This is easier. So let's look at even numbers. So remember, as we said, even numbers are divisible by 2. So this time we'll let n be 2k, where k is an integer, right? So if we, and it does have to be an integer because I just tried it with n being 0.3 and it definitely wasn't even, so it has to be an integer. So it shouldn't really say for all values of n, it should say for all values of n where n is an integer. Okay, anyway, so n equals 2k, we're back here. Like before, we whack it in, so n squared take n is 2k all squared, take away n, which is 2k, so that's 4k squared, take away 2k. Remember we said that if you can take out a 2, then it's even. So this is the same as 2k squared minus k, which is even. So hence, you must have a closing statement for n even, n squared take n is even, since 2k squared take k is an integer. Okay, So as you put down the bottom is an integer. Okay, proof 1 done. Deduction. What about this one then? So the equation kx squared plus 3kx plus 2 is 0 has no real roots. Prove that this inequality satisfies. Now you've done a lot of work for this. As soon as you see no real roots, hopefully you're thinking discriminant. So b squared minus 4ac must be less than 0. Okay? It's got a little twist on it though with this inclusive inequality here. So let's do this nice and quick. So b must be 3k, minus 4a must be k, and c must be 2. So we get 9k squared minus 8k less than 0. We have to factorize, don't we? Okay, now critical values, k is 0, k is 8 over 9. Remember, no graph, no marks. It's an inequality problem. So we got 0, 8 over 9. It's a positive quadratic. It's less than 0, so you go down the curve. Okay, some x-axis to curve. So we know that k must be between 8 over 9 and 0. But notice it's inclusive here, okay? It's inclusive. So what does that mean? They're obviously, sorry, it's not inclusive here, but in the proof it wants us to prove it's inclusive. So we need to investigate what happens. So what is happening then at k equals 0? Well, if we put k equals 0 into the original, right, so 0 times x squared plus 3, 0 times x plus 2 equals 0. So at the moment, I've got 0 plus 0 plus 2 equals 0. Ah, no, we've just broken maths. That's not true, is it? So k cannot be 0 as well. If k was 0, then we would still get no real roots. It wouldn't work. So therefore, k must be bigger than or equal to 0. And then you'd finish off. So it's also k is less than 8 over 9, and then you can put them together. So 0, 8 over 9. Okay? Next. How are we doing for time? Okay. So exhaustion this time. It's going to be not that long a video. Prove all square numbers are either a multiple of 4 or 1 more than a multiple of 4. So this is exhaustion this time. So notice deduction. We had to prove something was true. But exhaustion, we're going to prove it's true by doing all the possibilities. Okay? All the possibilities. So just like before, all square numbers are either a multiple of 4 or 1 more than 4. So we're going to have to look at odd numbers, aren't we? So odd numbers first. Let's try this. So odd number squared means, so if we let n equal 2k plus 1 again, where k is an integer, then n squared is 2k plus 1 squared, yeah, which is 4k squared plus 4k plus 1. Now, is that a multiple of 4 or 1 more than a multiple of 4? Well, if it's a multiple of 4, then I can factorize 4 out. I can for the first two parts, but I can't for the second part. So this is true, isn't it? So this is a multiple of 4 or 1 more than 4. This is, so hence, when n is odd, n squared is a multiple of 4 plus 1. Can you see? At the end. So we're doing exhaustion because it's either an odd number or an even number. So now we have to prove it for even numbers too. So even numbers, let n be 2k instead of 2k plus 1, where k is an integer. And therefore n squared is 2k squared. So n squared is 4k squared, which you can take out a factor of 4 of, okay? And therefore, hence, when n is even, n squared is a multiple of 4. 4, so statement is true. by exhaustion is full is true. Sorry, my writing really sucks. Okay, so exhaustion. By the way, exhaustion, just to really reiterate what exhaustion is, exhaustion could be something like, I don't know, prove that there are only, let me quickly do it, two, three, 7. There are only 4 prime numbers between 0 and 10. And I'll go, well, I'll check it basically by exhaustion. I'll look at it. So 0, no, that's not prime. 1, 2, 2 is the first prime. 3 is. 4, 5, 6, 7 is. 8 isn't, 9 isn't, 10 isn't. Ah, right, so there is 4. So by exhaustion, there are 4. You see, I have exhausted all the possibilities. Final one then, counterexample, proof by counterexample. So this time I just need to find any example where this does not work. That's all we've got to do. So proof by counterexample that the sum of 2 consecutive prime numbers is always even. Okay, so similar to exhaustion, I'm going to try and find random ones. But by counterexample, I just need to find one thing that disproves this statement, okay? I need to disprove that the sum of 2 consecutive prime numbers is always even. So let's think about it. Let's think of some prime numbers. So 3 plus 5 is 8. Ah, that's even. So I can see why they're saying it. 5 plus 7. Oh, that's 12. That's even. Yeah. But why don't I try the first 2 prime numbers that come to mind? 2 plus 3. Oh, that's 5. Not even. Okay. Therefore, by counterexample, because I have provided an example that says, sorry, this doesn't work. By counterexample, statement not true. Okay. There you go. Now you're ready for the classwork.